Hi, and welcome back to the next video in the physics lecture series. Today we're going to be talking about parallel circuits, and here we are on the reference table with the rules for parallel circuits. Okay, let's get started on our first problem. Here we'll start with problem 24. Which diagram below correctly illustrates an operating circuit that includes a battery as a source of potential difference, two resistors in parallel with each other, and an ammeter that reads the total current in the circuit? Well, and we look at the four choices. We see that choice 3 is the correct answer. It is a correctly developed parallel circuit. We have a battery, an ammeter in the line, and two resistors in parallel on separate branches. Let's take a quick peek at why these other answers are wrong. Choice 1 is not a circuit. It's just two resistors connected in series. Choice 2 is almost correct, but they throw in a switch and it's opened. So it's missing the meter. And choice 4 is absolutely nothing. These are not symbols for anything. Although, to give them a little credit, the voltmeter is correct and the ammeter is correct. But these two symbols right here are in series with each other, even if they were supposed to substitute for resistors. Okay, let's take a look at the next one. In problem 25, we're going to be talking about meters. What is the minimum equipment needed to determine the power dissipated in a resistor of an unknown value? So we have a voltmeter as a choice, and its symbol is this squiggly line with the voltmeter jumping over. Remember the mnemonic, the voltmeter goes over the resistor. Think pole vaulting. An ammeter, here's the resistor symbol with the ammeter, the A in the circle following directly either before it or after it. And here's the mnemonic for that. The ammeter goes through the resistor. Think Amtrak stays on the track. The correct answer, which is a voltmeter and an ammeter, so you need both of these meters, and then of course the last incorrect answer, a voltmeter, ammeter, and a stopwatch. The stopwatch is irrelevant to this kind of problem. I highlighted this problem because I wanted you to see the drawing for the voltmeter and its mnemonic, as well as the drawing for the ammeter and its mnemonic. All right, let's move on to the next one. Okay, once again, we have a parallel circuit. In the electric circuit diagram below, possible locations of an ammeter and voltmeter are indicated by the circles 1, 2, 3, and 4. Where should an ammeter be located to correctly measure the total current, and where should the voltmeter be located to correctly measure the total voltage? This is the kind of problem where you have to know the mnemonic for voltmeter, pole vaulting. It goes over a resistor, as you see here in choice 3. And ammeter is in line on the track. An Amtrak, the train stays on the track, so the current will flow through the meter, but you will measure across or over pole vaulting, like pole vaulting, jump over. You will measure the potential difference from one side to the other. And that's why the answer is choice 1. Okay, let's take a look at another problem. Okay, here in problem 34, we're going to base our answer to the question on the following information. An 18 ohm resistor and a 36 ohm resistor are connected in parallel, which I have highlighted in green, with a 24 volt battery. A single ammeter is placed in the circuit to read its total current. Which diagram of this circuit is correctly drawn using the symbols from the reference table? So when we go through all the choices, we can see that the answer is in fact choice 3. You do have the two resistors in parallel to each other. You have a properly inserted meter, and you have a properly inserted battery. In the other three choices you could see, choice 1 is a series circuit, so it's not a parallel circuit. And even though it's a correct parallel circuit, this is not what they were asking for. In choice 2, this is an incorrectly drawn circuit. The ammeter is not ever supposed to be where the voltmeter is, and that's what they did here. And choice 4 is missing a battery. So it's not actually a circuit because it doesn't have a power supply. Let's take a look at the next one. In question 35, the diagram below represents part of an electric circuit containing 3 resistors. What is the equivalent resistance of this part of the circuit? Well, you are supposed to be able to identify that this picture is a group of resistors connected in parallel. And when you identify that this is a parallel circuit, you have to choose the inverse resistance formula to do your calculations. Let's take a look at how that's done. So 1 over R equivalent is equal to 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance. So you have 1 over 3 plus 1 over 4 plus 1 over 12. And that eventually equals 8 over 12. But it's 1 over Req equals 8 over 12. So you flip both sides and you get 1.5 ohms. Now I want to show you a trick. It's a rule of thumb. It's going to be very helpful for you in all future problems. There is a rule of thumb that shows us that when 3 resistors are connected in parallel like this, the equivalent resistance is in fact approximately, in some cases exactly, half of the smallest resistor in the group. So our group contains a 3 ohm, a 4 ohm, and a 12 ohm. After we did our math, you saw that we did in fact get a 1.5 ohm resistance. So 1.5 ohm is exactly half of the smallest resistor. Usually, when each of these resistances can divide into the largest resistance, then the math works out where the overall or equivalent resistance is half of the smallest resistance. Otherwise, it's approximately half, and that's still very valuable information. Okay, let's take a look at the next one. In problem 36, we have a circuit diagram shown with an ammeter A1, which reads 10 amps. What is the reading of ammeter A2? All right, so now we have a voltage here, which is, as of yet, unknown. We have a total amperage, and why do we know this is total? Because it comes outside the branches, or before the branches. And we have a branch current A2 and a branch current A3. So this is a fairly complicated problem which requires some back solving. So the first step, knowing the two resistances, 20 ohms and 30 ohms, you have to first determine the equivalent resistance. 1 over R total equals 1 over 20 plus 1 over 30, 5 over 60. Flip that one more time because it's 1 over, and you get 12 ohms. So now you know you have 12 total ohms in this problem. The second part is to use the V equals I times R to find what the battery is. It's not listed here, so you have to use the known current for the total of the circuit and the total resistance that you just determined. Doing that, using the V equals I times R, 10 amps times 12 ohms, you get 120 volts. Notice an amp times an ohm is a volt. And then finally, using Ohm's law again for the whole circuit, you find that I is V over R, so the total V over the total or equivalent resistance, and that gives you 120 volts over 20 ohms, which gives you the full 6 amps. So there's 6 amps of current going through ammeter 2. So if there's 6 amps of current splitting off from the original 10, how many more amps are going through here? That's 4. So 6 plus 4 will equal the original 10. That's a very important point. They could have asked you in another part of this question, what was the current flowing through both branches? All right, let's take a look at the next problem. In problem 37, we're asked to base our answer to the question on the information in this diagram. A 20 ohm resistor and a 30 ohm resistor are connected in parallel to a 12 volt battery as shown. An ammeter is connected as shown. So here is the first resistor, here's the second resistor, and here's the ammeter in branch 1. What's the current reading of the ammeter? So the first step we do is calculate I is V over R. So we take the full 12 volts, which is the same for each branch. If you're not sure where that rule comes from, that was right here. The voltage or potential difference across each branch is the same. It's the currents that add up and are different. And we divide that by the branch resistance, which is 20 ohms. So 12 volts over 20 ohms gives you 0.6 amps. And that turns out to be choice. Now, if a student chose the other branch, the 30 ohm, here they would have gotten an answer of 0.4. And you'll see it actually shows up in the multiple choice. And that's kind of a little sneaky trick that the Regents does. You think you got the right answer because you see it there, but you don't realize that you actually used the wrong information. So try to be careful. If you're looking for the branch current in branch 1, use the resistor that goes with branch 1. Okay, let's take a look at the next one. In problem 38, we're also asked to look at a diagram, and there's a 20 ohm resistor and a 30 ohm resistor connected to a 12 volt battery as shown. And here in problem 38 is the same question as 37. The diagram is the same, 12 volts in parallel with two resistors, 20 and 30 ohms respectively, and now they're asking for the equivalent resistance. Let's take a look at the formula. We have to use the inverse R formula, and we add 1 over 20 plus 1 over 30, and we get 5 over 60, and then we flip that one more time, and we get 12 ohms. Now, if you remember what I said in the last problem, it is a rule of thumb that the equivalent resistance of a parallel circuit is approximately half of the smallest resistor in the parallel group. So our equivalent answer is 12 ohms, and half of 20 is 10, and 12 ohms is almost 10. Of course, it isn't 10, and remember the caveat to that was if these resistors are multiples of each other, then it's most likely going to be half of the smallest one. But since 20 doesn't go evenly into 30, so it will not be precisely half. But the rule of thumb still works. And if you had to choose in a multiple choice problem like this one, you would know that you could pick the 12 directly, because you know that for 10 ohms to be the answer, it would have to be multiples of each other, and they're not. And then 12 is close to half, and 25 is not, and neither is 50. Thank you for watching, and we'll see you in the next video.